The death of multiplication. A standard 175 billion parameter language model now consumes less power than a household light bulb while maintaining 16-bit performance levels. This shift is not about simple compression, but a fundamental change in how we define a weight. By restricting every parameter to just 3 possible values, -1, 0, or 1, we have effectively removed the multiplication operator from the inference equation. This hardware-software alignment is why mobile chips can now handle reasoning tasks that required a server rack 2 years ago. The math behind this efficiency starts with the total elimination of floating-point arithmetic. The Ternary Advantage. High-performance computing has been held hostage by matrix multiplication, specifically the energy cost of moving 16-bit values from memory to the processor. In the BitNet B1.58 architecture, the weights are ternary. When you multiply a feature by a ternary weight, you are really just performing a sign flip, or a zeroing operation. This reduces the energy consumption of matrix operations by over 70%, because addition logic gates are significantly smaller and faster than their floating-point counterparts. We are essentially trading complex arithmetic for simple routing. This hardware efficiency becomes even more apparent when we look at memory bandwidth bottlenecks. Parity. Without precision, skeptics argued that reducing precision would destroy model perplexity, but the 2026 benchmarks for the BitNet 70B model tell a different story. In zero-shot tasks like ARC Challenge and Heliswag, the 1.58-bit model matches the performance of FP16 Llama 3 equivalents while using roughly 10 times less memory. This works because large models are surprisingly robust to weight noise, and the training process actually learns to pack more information into the sparse ternary structure. However, this parity is not a free lunch, as the training phase introduces a new set of constraints. The training tax. While inference is cheap, training these 1-bit models requires a specific technique called quantization-aware training. You cannot simply take an existing 16-bit model and truncate the weights without losing the logic. The model must be trained from scratch using a straight-through estimator to pass gradients through the non-differentiable 1-bit functions. This means the initial compute investment is still high, even if the deployment cost is low. Furthermore, standard GPUs are not actually optimized for ternary addition, which is why we are seeing a surge in specialized ASICs and NPU designs. This transition from general-purpose hardware to specific math kernels is the final hurdle. The signal under the noise. The shift toward 1.58-bit architectures signals the end of the GPU era as the primary bottleneck for intelligence. By merging the ternary advantage of simple addition with the emerging market for specialized ASICs, we can see that the competitive advantage in AI has moved from having the most total compute to having the best memory bandwidth efficiency. This means that for builders, the goal is no longer about finding the biggest cluster, but about optimizing for the specific NPU instruction sets found on edge devices. We're moving away from the brute force approach of throwing more electricity at a model to achieve reasoning. Instead, we are seeing the rise of sparse, high-efficiency logic that treats compute as a commodity rather than a luxury. Watch for the first major consumer flagship phone to integrate a dedicated ternary processing unit by the fourth quarter of 2026. Subscribe for more.